strategic deployment of the proportional plus derivative (PD) algorithm, enhancing response speed without integral-induced lag. The proportional plus derivative (PD) algorithm enhances control loop responsiveness by combining the immediate corrective action of proportional control with the predictive, rate-based adjustment of derivative control. This dual-mode strategy excels in applications where rapid response to changing conditions is critical, and steady-state offset can be tolerated or managed externally. PD controllers are particularly effective in batch, integrating, or high-capacity systems where time to stability is a priority. Core characteristics of PD control. Immediate and predictive correction. The proportional term responds directly to error magnitude, while the derivative term anticipates error trends by responding to the rate of change of the process variable. No integral component. Unlike PI or PID controllers, PD does not correct for steady-state error offset. It focuses solely on dynamic performance, speed, and damping. Acceleration damping. The derivative term counters sudden changes, effectively reducing overshoot and minimizing settling time in processes with inertia or delayed response. Functional mechanics and algorithm behavior. Controller output formula. The PD controller is typically defined as M equals 100 PB behind DC D TT 12, where PB is proportional band, D is derivative time, E sty is error, and DC dt is the rate of change of the measurement. Derivative on measurement preferred. Most modern PD implementations apply the derivative action to the measurement only, not to the set point, thereby preventing instability when set points change. No steady-state correction. Without integral action, any persistent load imbalance results in a fixed offset, which must be tolerated or externally corrected, e.g. through manual biasing or supervisory layers. Behavioral dynamics and performance considerations. Fast stabilization. The derivative term introduces a lead effect, allowing the controller to break the process before it overshoots the set point. Offset persistence. The absence of integral control means any residual error at steady state will remain. PD is best applied in systems where perfect tracking is not critical. Noise sensitivity. Derivative control amplifies high-frequency signals. Thus, the process variable must be free of measurement noise to avoid instability. Application guidelines for PD control. Ideal for large capacity or integrating processes. In batch operations, level systems, or thermal processes where aggressive offset elimination is unnecessary during transitions, PD offers faster stabilization than PI or PID. Use in set point ramping or predictable transients. When processes exhibit predictable dynamics, the derivative mode preemptively adjusts the output to meet future state demands more effectively. Avoid in noisy or fast cycling systems. In high-speed control loops with sensor noise or jitter, the derivative component may create unstable or oscillatory behavior unless well filtered. Advantages of PD control. Delivers fast, well-damped response, reduces overshoot and oscillations in sluggish or high inertia systems, easier to tune than full PID controllers, enhances control during rapid load changes or set point transitions. No integral lag, loop response remains sharp. Limitations of PD control. Cannot eliminate steady-state offset, requires tolerance or external compensation. Not suitable for noisy measurement signals, amplifies high-frequency fluctuations. Derivative action can become unstable if process dynamics are not well understood. Limited benefit in fast processes where response time is already short. Process type compatibility. Best suited for batch or integrating systems where precision is needed during transitions, high-capacity thermal or pressure loops with long lag times, processes where quick stabilization is more important than perfect set point matching. Less suited for systems requiring zero offset or high accuracy at steady state, noisy environments or analog sensors without adequate filtering, fast processes where derivative contributes little improvement. Conclusion: the PD algorithm is a specialized control strategy that brings speed and stability to processes where fast upset correction is essential, but absolute accuracy can be relaxed. By introducing anticipatory behavior through derivative action and combining it with proportional correction, PD control is a valuable tool in managing process dynamics, especially when paired with external setpoint strategies or supervisory control layers that handle offset correction independently. Strategic deployment of the PID algorithm, maximizing control precision through balanced response, accuracy, and stability. The proportional integral derivative PID algorithm is the most comprehensive and powerful control strategy available in classical feedback automation. By combining the immediate correction of proportional action, the zero offset enforcement of integral action, and the predictive damping of derivative action, PID delivers superior regulation across a wide range of dynamic conditions. It is especially suitable for complex processes requiring both precision and speed. Core characteristics of PID control: three-mode compensation. Proportional provides instantaneous correction proportional to the present error. Integral eliminates steady-state offset by integrating past errors. Derivative anticipates future error based on the rate of change. Unified algorithm response. The PID controller adjusts its output based on the magnitude, history, and trajectory of the error, creating a balanced response profile that is both fast and accurate. Tunable for performance or stability. PID allows flexible adjustment to prioritize error elimination, damping, speed, or energy efficiency, depending on process goals. Functional mechanics and algorithm structure. Controller output formula. Tadam equals 100 PB times E plus 1 I quach E dt minus D times dc bar dt, where minus PB equals proportional band, I equals integral time, D equals derivative time, E error set point minus measurement, dcd equals rate of change of measurement. Interconnected gains, all three modes scale with the same proportional gain factor, maintaining consistency in tuning behavior and reducing interaction during parameter changes. Balanced vector contribution. The combined gain vector of the PID algorithm lies between minus 90 degrees and plus 90 degrees in phase angle, allowing tailored response damping and recovery time optimization. Performance dynamics and control behavior. Rapid response with minimal overshoot. The proportional and derivative terms act immediately, reducing the rise time and preventing overshoot. Zero steady-state error. Integral action ensures that even persistent load disturbances are corrected over time. Predictive damping. The derivative term slows down the rate of change as the process variable approaches the set point, improving stability. Increased complexity in tuning. All three terms must be carefully tuned to balance speed, damping, and accuracy. Poor tuning may result in sluggishness, cycling, or instability. Application guidelines for PID control. Best for long response, high-capacity systems. Processes with long natural periods, e.g. distillation columns, thermal reactors, benefit from PID's ability to speed up response without sacrificing stability. Ideal where set point accuracy and fast recovery are equally critical. Applications like temperature, flow, and composition control in blending, refining, and energy systems often require all three modes to manage precision and agility. Use when integral slowness and proportional offset are unacceptable. PID overcomes the weaknesses of PI and P only by combining precision with quick convergence to set point. Advantages of PID control: eliminates offset with precision across varying load conditions, combines immediate, historical, and predictive error correction, optimizes integrated error IAE and energy consumption, reduces recovery time after disturbances or set point changes, adaptable to a wide variety of process types and loop dynamics. Limitations of PID control: more difficult to tune due to interaction between modes, sensitive to measurement noise, especially through derivative term, integral wind-up risk if saturation or manual override occurs, requires clean, consistent process feedback to avoid instability. Process type compatibility: most effective for temperature and pressure control in heat exchangers, boilers, and distillation units, composition and flow control in blending, batching, or continuous process lines, systems where disturbances are frequent and offset cannot be tolerated. Less effective for noisy or high-speed processes where derivative gain amplifies unwanted signals, extremely simple loops where PI or P-only control suffices, applications with frequent actuator limits unless anti-wind-up logic is in place. Conclusion: the PID algorithm represents the pinnacle of classical control, offering a robust, responsive, and accurate solution for regulating dynamic industrial processes. When tuned effectively, it enables high-performance operation across a wide range of scenarios, from slow-acting thermal systems to precision-driven composition loops. While it demands thoughtful configuration and clean measurement input, its versatility and control superiority make it the default choice in most modern control architectures. All the files uploaded by the user have been fully loaded. Searching won't provide additional information. Multivariable control, managing interaction across process loops, coordinating multiple inputs and outputs for optimal process performance. Describe interaction in process loops. In traditional single-loop control, each manipulated variable affects only one controlled variable. These systems operate in isolation and exhibit no loop interaction, making tuning, stability, and performance relatively straightforward. However, many industrial processes, particularly in refining, chemical, and energy systems, require simultaneous control of multiple outputs using multiple manipulated inputs. These are known as multivariable systems and are characterized by loop interaction, where changes in one manipulated variable can influence several controlled variables simultaneously, often in complex and unintended ways. Nature of interaction in multivariable processes. Cross-loop coupling. In a multivariable process, any single manipulated variable can impact more than one output. For example, increasing flow through one valve may change both pressure and level in separate areas of the process. Interacting loop example. In a 2x2 system with two inputs, M1, M2, and two outputs, C1, C2, each manipulated input affects both outputs. This means that adjusting M1 might alter both C1 and C2. Similarly, M2 will influence both C2 and C1. Dynamic and steady-state interaction. These interactions are defined both in terms of steady-state gain, long-term impact, and dynamic gain, time-based response. Even if steady-state effects are manageable, dynamic mismatches can still destabilize the system. Practical examples of loop interaction. Pressure and flow control. In pipeline systems, adjusting one valve for flow affects upstream pressure. Both valves influence both flow and pressure, creating cross-dependence between loops. Blending systems. Blending often requires control over both total flow and composition. Any change in one inlet stream affects both parameters, making variable pairing critical. Level and pressure in closed tanks. Increasing level can simultaneously raise pressure. If not properly accounted for, level adjustments can trigger pressure alarms and vice versa. Distillation columns. Among the most interaction-prone systems, distillation requires tight control over pressure, composition, and levels at multiple points. Manipulated inputs like steam, coolant, and product flow rates all affect several outputs simultaneously. Indicators of interaction and control challenges. Coupling gains. Gains in off-diagonal terms, e.g. K12 or K21, indicate interaction. If these values are non-negligible, process changes intended for one loop will impact others. Response coupling. Setpoint changes in one loop trigger unintentional responses in others, often leading to cycling, offset, or instability. Oscillation and instability. Without proper pairing and tuning, automatic control in one loop may disrupt performance in another, leading to constant corrective behavior between loops. Tools to analyze and quantify interaction. Relative gain analysis, RGA, a method for measuring the interaction between loops by comparing open loop and closed loop gains. Values close to 1 indicate minimal interaction. Values near 0.5 suggest moderate interaction. Values 0 or 1 indicate severe or reversed interaction and potential instability. Dynamic gain analysis focuses on the time response characteristics of loops. Even if steady-state interaction is low, mismatched response times can cause dynamic interference. Relative gain array, RGA matrix, a matrix representing interaction across all loop pairs, guiding optimal loop pairing decisions. And managing interaction in multivariable control. Optimal loop pairing. Using RGA, loops should be paired where the relative gain, LLIT, is positive and as close to 1 as possible. Avoid negative or extreme values. Tuning for decoupling. If loops have different speeds, tuning can help decouple their dynamics, especially by detuning the slower loop to allow the fast loop to dominate. Process design adjustments. Systems can be physically re-engineered, e.g., altering tank capacity or valve placement to increase separation between loops dynamically. Decoupling strategies, full decoupling, mathematical cancellation of interaction paths, complex and risky if gains change. Partial decoupling eliminates the dominant interaction path, more robust and easier to implement. Conclusion. Multivariable control is a sophisticated domain of automation where the key challenge is managing interaction among loops. Understanding how manipulated variables affect multiple outputs is the foundation of this strategy. By combining analytical tools like RGA, smart loop pairing, dynamic tuning, and decoupling, multivariable control systems can be stabilized and optimized for higher throughput, reduced energy consumption, and better product quality. This approach transforms interdependent process systems into harmonized high-performance control environments. Decoupling, strategic isolation of control loops in multivariable systems. Breaking interactive paths to restore independent loop behavior. In multivariable process systems, interaction between control loops is often unavoidable, particularly when multiple manipulated variables simultaneously affect multiple controlled outputs. When tuning adjustments and loop assignments are no longer sufficient to suppress this interaction, decoupling becomes a necessary engineering strategy. Decoupling introduces mathematical compensation into the control architecture, allowing each loop to behave as if it were isolated, even in the presence of strong physical interdependencies. Understanding when decoupling is required. Decoupling is not always needed. Its application becomes critical under the following conditions. Strong steady-state interaction. When relative gain analysis, RGA, shows values near 0.5, interaction between loops is severe. Neither variable dominates control and both loops affect each other equally. Match dynamic gains. If two loops have similar speeds, dead times, time constants, they can disrupt each other continuously. This increases the risk of loop instability or cycling, especially under automatic control. Process design cannot be modified. When redesigning the process, e.g., adding surge capacity, changing valve positioning is not feasible. Decoupling is the only alternative to reduce interaction. Tuning and loop assignment are insufficient. Even after optimal tuning or pairing based on relative gains, some interactions persist. These residual effects can be suppressed through decoupler logic. How decoupling works. Decoupling adds a computational network, often based on process models or empirical relationships, that mathematically cancels out the effect of one manipulated variable on unintended controlled variables. Full decoupling cancels both cross-interaction paths in a 2x2 system, effectively making each control loop behave as a single input, single output SI-SISO system. The result is true loop independence. Partial decoupling cancels only the dominant interaction path, typically from a faster loop to a slower one. This is more practical, easier to maintain, and less sensitive to modeling errors. Application criteria for decoupling. Relative gains near 0.5. This is the most critical trigger. When interaction is symmetrically distributed, neither loop can dominate and decoupling is often essential. Loops have similar speeds and gains. Systems where both loops are fast and high gain exhibit strong dynamic coupling, increasing the need for decoupling. High cross-gain paths, K12 or K21. If cross-path gains are comparable to direct path gains, then interaction significantly disrupts closed-loop performance. Negative or large relative gain values level to 0 or level 1, these indicate unstable or reversed loop behavior if left uncorrected. Decoupling stabilizes control directionality. Implementation considerations. Accuracy of process models. Decouplers depend heavily on the accuracy of gain estimates and dynamic behavior. If gains shift due to nonlinearity or operating changes, decouplers must adapt or risk instability. Adaptive or gain-scheduled decoupling. To handle nonlinear or time-varying systems, decouplers should include real-time updating or operate within defined operating zones. Robustness to change. Full decoupling is sensitive to modeling errors. Partial decoupling is more robust and typically sufficient in most applications. Operator visibility. Controllers should be transparent, and decoupler effects should be observable to allow manual override or troubleshooting when required. Benefits of decoupling: converts multivariable systems into decoupled equivalents, stabilizes loops that otherwise exhibit oscillations or positive feedback, improves loop tuning by isolating disturbance effects, enables consistent control performance across varying conditions, reduces commissioning time in complex systems like distillation columns. Risks and limitations: decoupling fails when process conditions deviate significantly from modeled behavior, may require re-identification or retuning when system characteristics drift over reliance on model accuracy, can degrade control if decouplers are not validated. Full decoupling is computationally and conceptually more intensive. Use only when necessary. Best practices use relative gain arrays RGA to identify whether full or partial decoupling is needed. Prioritize partial decoupling in fast, slow loop pairs where one loop clearly dominates. Avoid decoupling in systems with high natural decoupling, i.e., high dynamic separation. Continuously monitor performance metrics to detect when decoupler corrections drift. Conclusion: decoupling is a powerful tool for restoring control loop independence in multivariable systems experiencing high interaction. When loop assignment, tuning, and process design are not enough, well-designed decouplers can suppress cross-loop interference and restore stability. Whether through full or partial implementation, decoupling enables more precise and resilient automation in complex industrial processes.